In today's video, we're going to look at describing a vector space completely. This involves a set of vectors within the vector space, and this set of vectors is known as the basis. And we can also use this basis to determine what's known as the dimension of the vector space. The idea of describing a vector space completely involves a set of vectors contained in the vector space, and this set needs to be the smallest such set that perfectly describes this vector space. So this set is going to contain a set of vectors from the vector space that are linearly independent and that also span the vector space. And such a set is called a basis for the vector space. Now, basis is not unique. In theory, you can have an infinite number of bases for any given vector space, but what is always true is that the basis is linearly independent and spans the space. We're going to look at several bases. These are going to be called standard bases. So the standard basis of Rn is given by these n vectors, the vectors 1, 0, so on and so forth, 0, then 0, 1, so on and so forth, 0, and so on and so forth. These are called standard unit vectors. Standard basis for Pn is just the set 1, t squared, so on and so forth up to Tn. The standard basis for this vector space of M by n matrices is given here. And so these are just three standard bases, and these are going to be used quite often in our discussion of vector spaces, so they're fairly important. We are now asked if this set forms a basis for R3. Right, so remember, in order to form a basis, right, the set of vectors has to be linearly independent and it has to span the vector space. So let's first check for linear independence. And you should recall from the last video that this is easily done by setting up a matrix in which each column is one of the vectors. And then check its RREF. If we get the identity matrix, then this would be linearly independent. Otherwise, it'd be linearly dependent. So let's go ahead and check the RREF. Oh, let me redo that. And we do indeed get the identity matrix. All right, so this implies, of course, that S is linearly independent. Next, we have to check for span. Right, so that is check to see if S spans R3. Again, we set up a matrix in which each column is going to represent a vector. except now we're going to augment it with an arbitrary vector from our vector space. In this case, we want an arbitrary 3-vector. Well, A, B, C, where A, B, and C have to be real numbers. And again, we want to RREF this. Missing parentheses. And this is the matrix we get. All right, so we get the identity matrix on the left-hand side, and that's augmented with the vector 2a minus b minus c, a minus c, and then negative a plus b plus c. Well, this means that there is a solution of constants. So S spans R3. Right, it's linearly independent and it spans R3. So, yes, S forms a basis of R3. Now look at our first property, which says that if S forms a basis for a vector space V, then every vector in V can be written in one and only one way as a linear combination of the vectors in S. This is what allows us to perfectly describe a vector space, right? So this is why the basis describes a vector space. All right, so first, we know that every vector U in V can be written as a linear combination. Of the vectors in S, right? Because S spans V, right? Because S is a basis for V. So what we're going to do is we're going to say that we have two different ways in which we can write U as a linear combination of these vectors. Right? So we're going to say that U equals C1 U1 plus so on and so forth plus CK UK, and U also equals D1 U1 plus so on and so forth plus DK UK. Right, for all of the CI's and DI's being real numbers. Right, what we must show is that CI and DI are actually the same, right? So we want to show that all of these constants are identical, right? So C1 and D1 are the same, C2, D2 would be the same, so on and so forth. This would show that there's actually one way in which we can write U as a linear combination of these vectors. Now, since U is a vector in a vector space, what we have is that 0 is U minus U. But this is C1 U1 plus so on and so forth CK UK minus D1 U1 plus so on and so forth plus DK UK. Right? Now again, V is a vector space. Since S is a basis for V, that would mean that all of the vectors in S are also in V. So these U1, these UIs, right, are all vectors in a vector space. This allows us to write this as C1 minus D1 U1 plus so on and so forth plus CK minus DK UK. Right, but again, remember, this is equal to 0. And we know that S is linearly independent because it's a basis. That means that this can only have the trivial solution. All right, what that means is that Ci minus Di must equal 0 for all I, which of course means that Ci is equal to Di for all I. That is what we wanted to show. And so the proof is complete. There actually is only one way in which you can write any given vector in the vector space as a linear combination of the vectors in a basis. Our next property, if S spans a vector space V and T is linearly independent of V, then the following two statements are true. First, it is possible to obtain a basis S prime for V from S simply by deleting some of its vectors if necessary. Second, it is possible to obtain a basis T prime for V from T simply by adding some vectors to the set if necessary. Right? So in other words, if a set of vectors spans a vector space, we can make it into a basis simply by deleting some vectors if need be. And if we're given a set of linearly independent vectors in a vector space, it is possible to make that a basis simply by adding some vectors to it, if necessary. All right, so for the first statement, all right, so since S spans V, we know that every vector U within V can be expressed as a linear combination of the vectors in S, right? In other words, U is equal to C1V1 plus CKUK, so on and so forth, right, plus CKUK, where each CI is a real number. Shouldn't be CKUK, I'm sorry. It should be CMVM. Now, we have a couple possibilities. S can be linearly independent. If that's the case, so if S is already linearly independent, then S is already a basis. And we're done. Second possibility is S is dependent. Then we know that either V1 is 0, in which case we just eliminate it, or at least one vector in S can be expressed as a linear combination of the remaining. of the preceding vectors. In which case, right, we can eliminate the first such vector. Right? Either way, we now have a new set S1, which is a subset of S, containing m minus 1 vectors. And it still spans V. Right, to see why it still spans V, that's easy enough, right? First off, the identity, the 0 vector, doesn't help in the span at all. If you have a vector that's a linear combination of the preceding vectors, right, simply by eliminating it, doesn't change the fact that it's going to span, right? Because that one vector was already spanned by the preceding ones. Now, we have two possibilities, right? If S1 is linearly independent, we're done. All right, we have our basis. Otherwise, we will repeat the above process. In other words, we look for either the 0 vector, take it out, or we look for a vector that's a linear combination of the preceding ones and take it out. And we're going to keep doing this until we obtain a subset called S prime of S that is linearly independent. And thus is a basis. Right? For the second statement. All right, so by the way, that proves the first statement. For the second statement, what we do is form an indexed set, call it U, in which the vectors in T are followed by the vectors in S. Right? In other words, what we're doing is we're taking the vectors in our linearly independent set and adding vectors in a set that span the vector space. Now, since U spans V, right, it has to because we just entered our spanning set into it. We can apply the procedure that we just went over. This will give us a basis U prime of V. Right, now all we have to do is show that all of the vectors in T are still in U, right? In U prime, right? So we didn't eliminate any vectors in T. That's what we have to do. Right, the only way that a vector in U is eliminated is if it is either 0 or it is a linear combination of the preceding. Right, so since T is already linearly independent, none of those vectors will be eliminated, right? So none of the vectors in T will be eliminated. All right. This is because obviously none of those vectors will be 0. Otherwise, it's automatically linearly dependent, right? And also, you can't have a vector being a linear combination of the preceding vectors because T is linearly independent. Therefore, U prime will contain all of the vectors in T. And then we just say that U prime is our T prime, right? Just to say that T prime is a basis. And that proves the second statement. So to actually see how this is applied, let's consider this set of 4 3 vectors, right? And we're going to say that this spans a subspace W of R3. We want to find a basis for W from S. Well, since S spans W, right, all we're doing is looking to eliminate vectors from S if it is necessary. To make it linearly independent. Well, to do this, let's set up a matrix where each column of the matrix is a vector in S. And, big surprise, we're going to RREF this. Right? And so our resulting matrix is the matrix right? To make this set of vectors linearly independent, what we want to do is look at the columns which have only leading ones, right? So what we do is we look and we go, okay, well, column 1 has a leading 1. Column 3 has a leading 1. Right? The columns without leading ones represent vectors that can be written as a linear combination of the preceding vectors. So what we do is we just eliminate the vectors that are associated with the columns that, when RREF'd, do not have a leading 1. Right, since columns 2 and 4 in the RREF do not have leading 1s, vectors 2 and 4 in S are linear combinations of vectors 1 and 3. Therefore, they can be eliminated. Right, what we are then left with is S prime equals the set 1, 2, 3, and then 0, 1, 1. And this forms a basis of W. So that was how to use the first statement. To use the second statement, let's consider this set here, T, which is linearly independent. And we want to find a basis for R4 that contains these two vectors. It should be obvious that it is linearly independent. All right, so therefore, we just have to add vectors from a spanning set into T, and then proceed as we did in the previous example. Well, we looked at the beginning of this video of the standard basis. All right, so standard basis of R4 is this right here, right? Which means this spans R4. So these are the vectors that we're going to add to T. So let's now create a matrix in which the first two columns are the vectors that were in T, right? And then the next four columns are going to be the vectors in S. And again, let's RREF this. Right, so this is the vector we get. Or I'm sorry, this is the matrix that we wind up with. And again, what we want to look at is those columns that have leading ones. Right, so columns 1 through 3, right? And we know that column 1 and 2 had to be in there. And then also column 5. So what that means is we keep the vectors of column 1, 2, 3, and 5. And that would be our basis. And so there's our basis for R4 that contains the two vectors in T. Okay. Let's look at Theorem 3, which says if S spans a vector space, V, and T is a linearly independent set of vectors in V, then the number of vectors in S has to be greater than or equal to the number of vectors in T. All right, so first of all, since S spans V, then every vector in T can be expressed as a linear combination of those vectors in S. What this gives us then is V1 is equal to A11U1, right, plus so on and so forth, plus AM1UM, right, so on and so forth, and then Vn is A1NU1, plus so on and so forth, plus AMNUM. What we now do is consider the equation 0 equals C1V1 plus so on and so forth plus CNVN. Well, replacing each V, we're going to wind up with C1A11 plus so on and so forth plus CNA1N U1 plus so on and so forth plus CN A1N plus so on and so forth plus CNAMN all times UM. Now, all of these C's have to be 0, right? Because T is linearly independent. So, if we look at this system, I messed something up. This C here should have been a C1. I apologize. And then this A should have been an AM1. Right, okay, now I should be back on track. All right, this system here has only the trivial solution. Which means that M has to be greater than or equal to N, right? The number of equations must be greater than or equal to the number of unknowns. Right now, if the indexed sets S and T are both bases for a vector space V, then M is equal to N. Right? In other words, every basis for a vector space must contain the same number of vectors. So since S spans V, and T is linearly independent, right? We know this. From the previous theorem, we must have that the number of vectors in S must be greater than or equal to the number of vectors in T. On the other hand, though, since T spans V, and S is linearly independent, right? Again, because they are both bases, it follows that the number of vectors in T must be greater than or equal to the number of vectors in S. Well, there's only one way both of those statements can be true, and that is for the number of vectors to be identical, right? And we give this number of vectors a special name since all of the bases of a vector space must have the same number of vectors. We call the number of vectors in any basis for a vector space V the dimension of V, and is denoted as dim V. Let's take a look at Theorem 4. Let S be an indexed set of vectors in a vector space V with the dimension of V equaling n. Then the following two statements hold. If S spans V, then S is a basis for V. If S is linearly independent, then S is a basis for V. All right, so to prove the first statement, by statement 1 of theorem 2, we can obtain a set S prime, which is a subset of S, that is a basis for V by deleting some vectors from S. However, if we delete vectors from S, the size of the resulting basis would be less than the dimension of V, which can't happen. This means that S must already be a basis. And we're going to use a very similar argument. So by statement 2 of theorem 2, we can add vectors to S to create a basis. But doing so would give a basis with more vectors in it than the dimension of V, which cannot happen. So S must already be a basis. Right? In other words, if you have a set of vectors that have the same number of vectors as the dimension of your vector space, then if S spans V, it must also automatically be linearly independent. And also, if S is linearly independent, it must also automatically span the vector space. As a direct corollary to statements, a set of vectors in a vector space V that is linearly independent must contain no more than the dimension V of vectors, right? So you cannot have a set of vectors with more vectors in it than the dimension of V be linearly independent, right? So if you have a set of vectors with more vectors in it than the dimension of V, that set's automatically linearly dependent. Also, a set of vectors in a vector space V that spans V cannot contain fewer than the dimension of V vectors. In other words, if you have a set of vectors that contain fewer vectors in it than the dimension of V, then there's no way that set can span the vector space. All right, so let's conclude by looking at Theorem 5, which states, let V be a finite dimensional vector space with a subspace W. So this is important. This only holds for finite dimensional vector spaces. First, the dimension of W is less than or equal to the dimension of V. And secondly, if the dimension of W is the dimension of V, then W and V are the same. For the first statement, since a basis for W must be a linearly independent set of vectors in W it cannot contain more vectors than does a basis for V, right? Because W is a subset of V. That proves that the dimension of W must be less than or equal to the dimension of V. For the second statement, let S be a basis for W. Now, since S is linearly independent, is a linearly independent set of vectors within W, and keep in mind, thus in V, and it contains dimension W, which equals dimension V vectors, S must also be a basis for V by theorem number 4. Now, since W is equal to the span of S, and so is V, we have that W is equal to V. That concludes our video on basis and dimension. In the next video, we are going to look at rank and nullity. So we're going to revisit matrices and look at the rank and nullity. Now, to do this, we're going to look at 3 new vector spaces known as the column space of a matrix, the row space of a matrix, and the null space of a matrix. As always, thank you for watching. I hope that you've learned something, and I will see you all in the next video.